Fine. Okay, so we saw what is partition chromatography. We saw that it is basically the mobile phase also changes there. So liquid chromatography, gas liquid chromatography. So based on the partition coefficients of your analyte, of your solute. So basically chromatography, all types of chromatography, partition, adsorption, and the other column chromatographies, which we are going to see today, all of them, they rely on the same method, that there is always a stationary phase, there is always a mobile phase, that these two things will never change. So, and the interaction of your analyte with the stationary phase, the interaction of your analyte with the mobile phase, this is one of the key factors that will determine the separation also. So based on your analyte, you're going to choose the stationary phase and the mobile phase. So proceeding further, last time we saw, so today, sorry, so this time we are going to see ion exchange chromatography, we are going to see gel permeation, or which is also known as size exclusion. And then there is one more, affinity chromatography. So we are going to see the three other chromatography, and this is like a schematic representation where you'll see that this chromatography, the adsorption part, we are going to also discuss this after we finish today's three chromatography techniques. In the next class, we're going to see adsorption chromatography. From partition, we have seen paper chromatography. Thin layer also we are going to discuss. Okay, so again, just brushing up the basics is, what is the difference now? Adsorption chromatography, partition chromatography. Here we saw that we are working on the partition coefficient of your analyte. So you have been given a mixture of things and you have to separate one of that. It's not so easy, and that's why we are taking the help of this technique to separate your analyte of interest from the mixture. So again, there is a stationary phase, there is a mobile phase. In partition chromatography, your stationary phase is liquid. We saw that in the paper chromatography, when you put your paper in the solvent mix, which is a mixture of solvent and water, the paper absorbs water and the water runs over the paper. Now that is your stationary phase. The water is your stationary phase. Now water is bonded to a solid surface, and this solid surface is your filter paper. Okay, and your mobile phase is also liquid. Now your stationary phase is also liquid, so hence it is also called as liquid chromatography. The same can happen with gas, where gas becomes your mobile phase. Okay, and the stationary phase is always going to be solid there, which is a paper. So if you look at this diagram here, the solute dissolved in liquid phase bonded to the surface of the column. So your support is going to be there, and over the support there is going to be a layer of the stationary phase. In adsorption chromatography, again there is going to be a stationary phase and a mobile phase, both of them. The mobile phase can be liquid or gas, just like partition chromatography, but here it works on physical bonds. So the analyte, or whatever mix of things you're going to add to the column that is to be separated, is going to bind to the stationary phase. So the soluted adsorbed. So adsorption is your particles, the molecules of your interest are going to sit on the stationary phase. They're going to interact, they're going to bond. Now more the bonding, more the strength of the bond of the analyte that is formed with the stationary phase, slower it will move, and hence it can be eluted later. So moving further, today we are going to see size exclusion chromatography. It is also called as gel permeation, and it is also called as gel filtration chromatography. So we are more interested in discussing about, say, proteins, because biochemistry, biotechnology, we will always be dealing with separation of biomolecules from a given mixture. Now, these biomolecules can be produced by bacteria, or they can be extracted from some other living source, or you can even artificially make them in the laboratories. So you can synthetically also synthesize them. So chromatography, again, what are we doing here? We are actually working on separating. So again, emphasizing that it's a separation technique, and out of many biomolecules, one biomolecule or one compound, a specific drug, a specific metabolite, a protein. So basically, you can have a mixture of macromolecules and micromolecules. So these macromolecules, they can be proteins, amino acids, and micromolecules can be, say, some ions. So separation of these from your mix is what you want to achieve, and you can take help of some techniques to achieve that separation. So now when we talk about size exclusion, so see, look at this word size. So it means that this kind of approach is exploiting the character of the biomolecule. So now your biomolecule has a certain size, it has a certain molecular mass. Okay. Now this mass of the protein is the property that you're going to exploit and do the size exclusion chromatography. So when you are given an extract, so that extract can be a mixture of small molecules, big molecules, different types of molecules, and they are going to be of different molecular masses. So this technique is used to separate these different sizes and these two different masses or three different masses from each other. Now you can also use electrophoresis to do the same. Okay, electrophoresis technique is also a separation technique, which is another part of this unit that we are going to see. It is also a very sophisticated separation technique. But what happens in electrophoresis is that the purified and the separated protein cannot be further used, because, for example, if we are talking about SDS page, which is another type of electrophoresis specifically used for proteins. We are going to see what is it later, but I'm just mentioning it here so that when we do that part, you will be able to correlate. So when you do SDS page, what you do is you denature your protein. So whatever protein you have, so protein is only functional also, I told you all, because it has a specific configuration. It has a specific structure. Why? Because these are long molecules and they have been folded in a certain way. And if their fold is disrupted, then they become dysfunctional. So when you denature them, basically you're treating your protein with SDS, which is a surfactant, sodium dodecyl sulfate. It's a surfactant. You're treating the protein with a surfactant. The protein unfolds when you treat it. It denatures and it loses its function. So then that protein, which is now not functioning, you cannot use it for certain experiments, further experiments. There you can only detect what is the molecular mass of the protein. You can detect there. In electrophoresis, you can separate it, but the separated protein is of no use for you now because it has lost its activity. So what is a protein? How is a protein useful when it has no activity? But in size exclusion chromatography, the advantage is there. The advantage is that whatever protein you are going to elute from the column, that can be used for further experiments. It is not going to be denatured. Okay, so then that is one advantage over electrophoresis. Now we are going to see how, again, what is the stationary phase and how the stationary phase is so important. Now when I mention molecular mass, the protein's molecular mass is always mentioned as kilodaltons, which also is written as kDa. It is not in mg, grams, but the molecular mass of proteins, the unit is kilodaltons. So now this term you will be frequently reading in your books, or even in the slides also you're going to see this word. So now the different proteins again, larger the size of the protein, larger the mass of the protein, larger will be the kilodalton value. So it can be 60 kilodaltons, it can be 70 kilodaltons, it can be 80 kilodaltons, and the smaller ones can be 1 kilodalton. In some videos they also use this word keda, just like a short form abbreviation. So 2, 3, 4, so there's a range, and based on that size of the protein you can choose your stationary phase. Now this you can see that it's again there is going to be a column. So this is the column here. Now this column is filled with stationary phase. Now this stationary phase here is in the form of beads. Okay, these are in the form of beads. Now there are certain properties that this stationary phase must have. What is one of the property? It must be inert. The stationary phase must be inert material. What is an inert material? Can you all answer in the chat box? What do you understand by the meaning of inert? So please don't waste the time. Please answer quickly so that we can move further. What do you mean by inert? Anybody?
It is unreactive.
Yes,
It
it is.
doesn't react.
Yes, very correct. It is unreactive. So this bead has to be unreactive, because if it reacts with your solute mix, the analyte that you want to separate from the solute, if it starts reacting with that, then there is no meaning, because then you will not be able to separate the analyte, or the analyte's chemistry will change. Okay, and hence then it will be of no use for you. So basically it should be inert, that does not react with your analyte also, and it should not react with your mobile phase also. So should not react or interact with mobile phase. And yeah, so it has to be inert in nature. Analyte interact with the analyte in the sense that it should not transform the analyte. It should not change the conformation completely and make it inactive, or make it dysfunctional in such a way that it cannot be used any further. So these molecules, these beads are inert material. They're commercially available also. And now what are they made up of? These beads are heteropolymer. The column chromatography, all of them are actually containing polymers only, most of them. Some of them are natural polymers, some of them are synthetic polymers. So the packing material is always a polymer. But in this case, now you see that these are heteropolymers. Why am I saying heteropolymers? Hetero, the word means is different. Okay. So you're going to have beads of different pore sizes. The beads that you are going to fill in the column, they are going to have different pore sizes. So some may be large, some may be medium, some may be small. So that's why the word is hetero. So if all the beads had the same pore size, then you would have said that this is homopolymeric. But this is heteropolymeric because the bead sizes are the pore sizes on the beads are going to be different. Okay. Now, since it is the stationary phase should not interact with the mobile phase. It should not completely transform the analyte, but now there is an interaction between the beads inside the beads also. So how are these beads? The beads are having pores. Now there is certain why do they have pores? Because now these are polymeric materials. Okay, so suppose these are the particles. I'm talking about within the bead. Now what is going to happen is these are going to bind to each other. There's going to be a linking. There's going to be a linking between these particles. So this is known as cross-linking. They're going to cross-link with each other. And when they cross-link with each other, they form a, so they're connected to each other. So it means that there is going to be a network system. So I've just drawn like 2 rows. Now imagine that there are 3. So they are going to be in touch with each other. So there's going to be a networking system within the bead itself. Okay, within the bead, there's going to be a networking system. It will form a mesh-like structure inside. Now, if like I can draw it here. Again, I said that these are heteropolymers. So it means that in some cases you will see, like if this is the bead, then you can see that the pore size, what I was talking about. So this can give rise to larger pore size. Now, if there is very intricate networking, very close bonding, so whatever pore size you're going to get is much smaller. So I'm not drawing it completely. So it is somewhere like this, very intricate, and the smaller particles in your protein mix or the smaller particles in the mix that you have been given are going to fix inside here. So these will be smaller pore size. Okay, so based on this kind of cross linking and how the network is formed, the molecules that you're going to add will entrap in these pore sizes. Okay, the larger molecules definitely will find way in the larger pore sizes. The smaller molecules mostly will also go in the small pore sizes, but because of their size, because of their mass, they will also be able to enter into the larger network system also. So both are made up of the same material, but the pore sizes, now both the type of beads that you saw with large pore size and small pore size, they are made with the same material, but what is varying is the pore size that is varying. Okay, now when you're packing the beads in the column, now see, for example, this particular column I'm talking about, do you see some gaps in the column? Are there any gaps? So if I color it, say with green, what are they? Are they the gaps between the beads? Yes. So these
Yes,
are the,
ma'am.
yeah, yes, these are the gaps. The columns are definitely going to have gaps. Okay, and these gaps are called as, gaps is a common word, but in column chromatography, voids. Okay, they are called as voids. Now, whatever you are going to pour, whatever mobile phase you are going to pour inside is going to occupy these voids also. It will also enter the bead, it will also go inside the bead, but at the same time, it is also going to run through the gaps. Now, this volume of your mobile phase that is going to run through the gaps can also be called as the amount. Okay, you can also say that some of it is going to pass through the void volume, some of it is going to go through the beads also. Okay, so now we will basically start with how things work in the size exclusion chromatography. Now, if you have a protein extract and if you pour that protein extract on the beads, so pouring is the word that we use here in chromatography. Pouring of your sample is also known as loading of your sample. Okay, so you load your sample on the polymeric bed or on the bed of the stationary phase. So like this, you're going to load your sample, and for loading the sample, you're going to use a micro pipette in column chromatography. But if you're doing HPLC, even that is a type of chromatography. If you're doing gas chromatography, you don't use micro pipette, you use a syringe, you inject your sample in the column. Okay, now here you're going to use a micropipette to load your sample. So addition of your solute mix, addition of the mixture from which you have to separate the protein or any other molecule, that process of addition to the column is known as loading of the sample. Now if you have different size, different pore sizes, if you have beads of different pore sizes and you're going to add your extract, you're going to load your extract on this layer. Now what is going to happen? The larger ones, the larger molecules, the larger protein molecules will go in the larger mesh, larger pore sized mesh, and the smaller will go in the smaller respective. Okay, so here itself we are now understanding how it works. Like larger molecular mass is going to go into the larger pore size, the smaller is going to go in the smaller. Now your volume of beads that you have already added, whatever you have added here, is going to be fixed. So say volume of beads is fixed. You don't change it. Once you pack the column, you're not going to say after 2 hours, okay, let me add more beads into it, or let me take out some beads from the column. You never do that. So your volume of beads is always fixed. Now what changes in this column is your volume of mobile phase, okay, mobile phase, and the void. The volume of the void also changes. Okay, so sometimes this void is occupied by molecules, protein molecules. Now after you load your sample, this sample which is red color here is going to move down also. So this sample will have different sizes. The sizes which will be able to enter into the pores of the beads will go and sit inside, but the ones which do not have the suitable size may just remain outside in the void. Okay, now your mobile phase will not easily trickle down. Your mobile phase will have to pass through these molecules and the path is not going to be clear. So that is why I'm saying that the void volume will change, but what does not change is the volume of the beads. Okay, now the mesh within the bead is not straight. See, if you look at this particular bead here, how is the mesh? Is it just like straight? No, it is not straight. If it was straight, then it was very easy for the molecule to pass. How? Because it would just have gone past straight like this in a straight path. But now because it is zigzag, your molecule may enter in from here, then it may pass like this. It will take a course, it will take a route, and then finally it will be somewhere out like this. Now as it goes out, again there is another bead here because you have too many beads, right? Now this molecule will enter again in the network. Again there will be a zigzag network. Whatever it is, it will find its way and come down. So see, this is just one bead. Maybe the picture here is only focusing on one bead. But if you see the larger picture, there are beads in rows. So your molecule of interest will have to pass through this first bead, second bead, third bead, fourth bead, fifth, and then it will be eluted. So it's not an easy course. The separation is not going to happen in fractions of seconds. The separation will take time because the path that the molecule follows is not so straightforward. Okay, it is going to pass through the zigzag network. So protein is going to basically move very slow. It could be a protein, it could be anything that you're separating. Your analyte is going to be slowly moving through the beads. The larger molecule will move through the voids because maybe depending upon the pore size, when you add your sample inside, the larger, if the molecules which are large, if they do not find a suitable pore size bead, they are going to remain in the void only, because in a larger pore size. So suppose if this is my network, mesh network, okay, so this thing is going to be my pore size, right? This is the pore size, suppose. So what is going to happen in this? A large one may not be able to enter because of the size, but definitely if there is a small protein of this size, that will be able, that is easily able to enter into the pore, but a larger one may stay outside, larger one, larger than this pore. So that's why, where will it stay? If it does not enter into the bead, it is going to stay into the mobile phase only. So the mobile phase will be having a lot of large molecules, and the small ones will go into any bead, because they are small, they can enter anywhere. So the larger molecules will move through the void and then stay for some time. Some might stay in the column itself, or some might just get entrapped. So some of them might just get entrapped like this between the beads. Okay, so it is difficult for them to get out. Some of them may easily come out and can be eluted now. Now, if you talk again about the column chromatography, last time I told you that mostly they work on the gravitational force. So they are going to, under the influence of gravitational force, the movement of the mobile phase is always going to be from top to bottom. The movement of your proteins or your compounds or your analytes, whichever you're going to load, is always going to be in the downward direction. Okay. So as I told you now, that the mass of the proteins here is always measured in kilodaltons, and that property we are going to exploit. So the commonly used gel, or the commonly used matrix, you can say the word matrix. So these beads, so the term here can be matrix, is basically in size exclusion chromatography is Cephadix gel. Okay, we are going to see one video where there's a student who is demonstrating how gel permeation chromatography is done. So now you have different sizes of different molecular masses of protein. So based on that, there are different types of Cephadix that you can use. Yeah, so these are the ones. So you have Cephadix G25, Cephadix 100, Cephadix 200, and this is telling you what polymer it is. It is, these are, so first three, dextran, polyacrylamide, and if you look at Cepharose 6B, Cepharose 4B, they are made up of agarose. So your matrix is basically here dextran, 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 but what changes here is the pore size, because now if you are using Cephadix G25, now if you have a mixture of substances, of molecules, okay, whose kilodalton, whose molecular mass is ranging from 1 to 5 kilodaltons, you don't need to use any of these. If you know that you're looking for an analyte whose molecular mass is between this range, then you should always go for Cephadix G25. These are the commercial names. These things are available and then you can order them. So by this commercial name, it is available, Cephadix G25. It is made up of, the polymer here is dextran, and the pore size is good for separating your analyte, which ranges from 1 to 5 kilodalton. If you have something of a higher range, then you can then choose your matrix based on that. Okay. Here also, I was telling you that the path is never straight. So now it's not like the molecule enters like this and just passes out. No, the path is never straight. The path is never straight inside the bead also and outside the bead also. So here also, here it might move like this in a zigzag fashion, and inside also it might move in a zigzag fashion, and hence the separation is slow. The movement of the molecules is slow. The slower molecules and the larger molecules will travel at different rates. In the voids, like in the gaps, you can see that these are the gaps. The large molecules will travel through the voids, through the gaps, and then that can be eluted. Okay, so this is basically how the size exclusion chromatography works, or you can say the gel filtration chromatography works. So in the other picture here, there are some more details, like the stationary phase is a three-dimensional lattice formed by a porous gel. So the gel may consist of cross-linked polysaccharide chains sold under the brand name Cefidex. So Cefidex is a brand name, or you will also see Biogel, which is polyacrylamide. So these are the brand names given by the companies. These products are supplied as dry powders. So when you get them from these vendors or from these companies, you get them as dry powder, free flowing powder. Okay. But they should not be exposed to the atmosphere. So when you store them, you have to make sure that you have closed the container properly. Uh, and then you keep it in a place where it is not very moist, it is not very um, humid. Okay, keep it in a dry place. Keep, especially you can store them at room temperatures also. The conditions will be mentioned on the bottle. You can store them in cold conditions also, but they have to be dry because they are hydrophilic beads, so they swell in water. Okay, they swell in water, they swell in buffer to form a gel, and then the pores in the lattice can be thought of as a series of traps. So basically you are entrapping the protein molecule inside the beads. So this, they, when they cross link, they are forming that network, the mesh network inside. What are they? Basically, they are traps or pockets. So the size range of the pores in these products can be varied by adjusting the degree of cross-linking or polymerization. And lower the degree of cross-linking, larger will be the pore size. Higher the degree of cross-linking, smaller will be the pore size. So based on that, then you can separate. Again, while you pack, it's a column chromatography, so you will have to, you also get ready-made columns. Okay, but they are very, very expensive. So most of them prefer to order these dry powders and pack them manually in the laboratory. So while packing, you have to make sure that you just don't pour the powder directly in the column. First, you need to equilibrate the column. Equilibration is whatever is your mobile phase going to be. Usually when you're working with these biomolecules, pH is a very important factor, because if your pH is not suitable, the molecule may lose the activity, the molecule may change the conformation. So that's why, to avoid all of that, you must have an optimum pH buffer. So if you're working with any protein molecule, that protein molecule is going to have a pH of say 7. If it is functional at a neutral pH, then you must have a buffer which is of pH 7. So something like trisaxial buffer, which comes in a various, you can make a trisaxial buffer of different pH also. So choose a buffer which is of a neutral pH. Now, this polymeric powder which you get is now added to the buffer. Before you pack the column, you need to keep them to swell in the buffer. So it will absorb the buffer, it will equilibrate. Now, the pH of your beads outside is also going to be 7, inside also it is going to be 7. Why? Because now the buffer has seeped inside through the pores. So your protein molecules of interest will not have a different environment outside the bead and inside the bead. So this equilibration is very, very important. And then after equilibration, you pour the slurry. It becomes a slurry. You pour the slurry in the column. So before that, degassing is also advisable. Why? Because there can be air pockets while you're making a slurry, while you're equilibrating. Air also is there. And to remove that air, degas, it means that remove the air molecules from the slurry, and then you can pack it into the column and then load your sample on the beads. Now, another very important thing is that your, see, if this is the bead, okay, I'm talking about the bead numbers, column number second. If this is known as the bed, bed of the stationary phase, okay, gel bed, you can also call it as gel bed. Your buffer level has to always be above the gel bed. You must always pour, even if you're not using the column, you have packed the column today, and suppose you think that, okay, my sample is still not ready to load, my sample will be ready to load tomorrow. In such a case, you have already packed the column, but you decide to use the column on the next day. So what do? You never keep it dry. You always pour your mobile phase, which is going to be a buffer, you pour it above the gel bed and keep it moist, keep it wet. Because when they dry, obviously, then what will happen? They will lose water and they will start shrinking and they will become dry. And a dry column is never preferred in column chromatography. You should always have a properly equilibrated moist column. So these are some things that you must take care of while you're doing column chromatography. Now, these are some questions. Which proteins elute first in size exclusion chromatography? Of course, we just saw that the larger ones, they sit in the voids. They may actually be the first one to come out. So the larger one will be eluted first in size exclusion chromatography. And the smaller ones, which have more accessibility to the different beads, because even if the beads, even if the pore size is larger, the smaller one can easily enter in those beads. So they will take a relatively longer time to come out. What is the main purpose of size exclusion experiments, chromatography experiments? So basically, based on the size, this gel filtration method can selectively choose and separate selectively the specific sized molecules. So separation occurs here when you have a mix of different molecular masses, different mix of molecules of different sizes and masses. So some of them will be retained and some of them will be removed. So some of them will be included and some of them will be excluded from the pores within the matrix. And that's why the name comes as size exclusion chromatography. So based on the size, some of them will be included inside the beads and some of them will be excluded outside. What is the stationary phase in size exclusion chromatography? So every type of chromatography is going to have a stationary phase and a mobile phase. So here you are going to have these beads, the trapping beads of smaller molecules in the pores of the adsorbent. So your stationary phase is going to be those polymeric supports, and this process is usually performed within a column, and it typically consists of a hollow tube. So you saw how the column looks somewhere very closely resembles, since you haven't seen it yet in the laboratories, but it is somewhere very close to how a burette is. A burette is much longer actually, but in the column chromatography, you will see that you're working on smaller lengths or smaller heights of the column, because obviously you're working on biomolecules and you never get too many biomolecules, too much of it. So you have to really work say into 2-3 batches to extract that size of your sample. Secondly, we are using commercially available polymers, and which are very expensive. So you cannot pack a really big tall column. You have to work on smaller volumes because they come very expensive. Most of these column, most of the matrix is actually reusable. So it's not like you use it for the first separation and you throw them. No, you can give them washes. You can remove whatever is adsorbed or has been in the beads, and you can give them good washes and you can reuse them at least for second time. Now stationary phase here is, we saw that they can be polyacrylamide gel, it can be dextran. So basically these are polymers of very small sizes. Size how small? Actually micron scale polymer beads, okay, of different pore sizes. Can they be used? Can this type of size exclusion chromatography used to purify proteins? Yes, it is one of the simplest and the mildest methods. Why does it say mildest? Because it is not interacting and changing the conformation. It is not using anything very harsh. It is working on a simple principle of separating them on the basis of their molecular mass. The chemistry is not altered. The biomolecule chemistry is not altered here, and that's why it's a mildest method of protein separation. No harsh chemicals are used. It's just working by using buffers. And yeah, it is actually one of the final steps in a purification protocol. So whatever you're going to get, definitely you're going to get a pure form of your analyte. So how is it done? So you can look at this particular GIF image here. You can see that this is how This is the polymer, and you will see the networking, the mesh inside. So these are the entry points for a protein molecule. So this is just one bead, any biomolecule. So this is quite a large pore, so small molecules can enter inside. Small molecules can enter in the larger pores. But now look at this one, which is a very small pore. So in these small pores, the large ones may not be able to enter. So where will they stay? They will always be found in the voids, in the gaps. Okay. I want to play this, but
welcome to my video series of biotechniques explained in 5 minutes, where I explain the concept of biophysical technique in less than 5 minutes or so. If you haven't yet subscribed to my channel, hit that subscribe button. I'm also present in Unacademy, which is India's biggest online learning platform. Use my code AB10 to get a 10% discount in that platform. Their size and sometimes which you can separate the proteins.
Ma'am, the video is not visible.
Sometimes the molecular weight.
Sorry, I'll have to go back to. Now is it visible?
Yes, ma'am.
Just like any other column chromatography, the workflow is very similar. It starts with equilibration state, followed by a binding state when the protein or the annihilate is binding to the column, followed by a wash where the non-specific binding are removed, and then the elution step when you sequentially get your purified fraction eluted. Now, let's see how gel filtration chromatography is very different from other types of column chromatography. So gel filtration chromatography has the column packed with beads which are porous. Now these beads are either made up of agarose, which are known as saffrose beads, or let's say dextran, or let's say polyacrylamide. All of these cases, it has pores inside it. So the protein samples, which are very small in the size, they can really enter the bead. And as they move through the column, they're actually retarded because they're moving slowly through these beads. So any protein molecule which is smaller in size can enter the bead. Whereas the protein molecule, which is bigger and cannot get inside the bead, would try to squeeze its way through the interspace between the beads. So a big protein molecule do not enter the bead. And they are not retarded, rather they move faster than the small protein molecules. Based on this mobility, these are collected in separate fractions. Now, there is a particular term known as exclusion limit. It's a cutoff size beyond which a particular protein or a biomolecule cannot enter the pore of the bead. Below that, it can enter the pore of the bead. For example, if we say the exclusion range is 0 to 700 Dalton, anything below 700 Dalton can enter the bead, whereas anything above 700 Dalton cannot enter the bead. So based on the differential mobility, based on how proteins enter the bead or they don't enter the bead, we can get a size exclusion of these proteins, right? Now, there are various type of beads which are available in the market, such as Cefadex, which is based on dextran, Biogel P based on polyacrylamide, or Saffrose, which is based on agarose. Now, the proteins which are bigger size, you can clearly understand they would be eluted quickly in the elution step, whereas the protein with smaller size, which has already entered the bead, they would be retarded and hence they would be eluted later. And that is how we can separate between them based on their size. Now, let's talk about few volumes, because these chromatography is semi-quantitative and we can also have a rough idea about the molecular weight of the annihilate or molecular weight of the protein we are trying to separate. So the volume which is inside the bead is actually known as the internal volume, or VI, whereas the void volume means the volume which is occupied by the interspace between the beads, which is known as V0. Now, void volume and the internal volume are actually related to the elution volume by this equation. The relative elution volume, which is like VE by void volume, is actually a function of the log of the molecular weight of particular protein. So by plotting a graph between them, we can extrapolate what is the molecular weight of our protein of interest. Let's say we have few standards such as PSA, cytochrome C, etc., which have different molecular weights, and we construct a standard curve. From that standard curve, we can determine what is the molecular weight of our particular protein of interest, because we always get the information about the elution and the void volume of a particular experiment. So from there, we can really calculate.
Okay, so void volume some problems here. Sorry. I'm unable to actually click hub. Okay. So here you have VO, V0 actually. Void volume, the volume of buffer, the volume of your mobile phase, which runs through the gaps. Okay. And then you have a column's total volume. What is the total volume of the column? So that can be represented as VT. Okay. So this, the total volume of a column is plus, which is your void volume, plus your VL, that is the liquid mobile phase. So this is the volume of the beads, the stationary phase. So this is important to remember. So your total volume of the column is the volume of the beads, the volume of the gaps, and the volume of the mobile phase that passes through it. Okay. Even if you remember this much, is enough at this stage.
SQL or SQL is an
We're starting with gel filtration medium. This is Cefadex.
So this is sigma that provides extra pure material. That is your stationary phase. That is Cefadex. The dex stands for dextran, and Cefadex is the commercial name. So dex, if there is a dex, which is a suffix here, you must know that the polymer material is going to be dextran. If it is agarose, then it is cepharose. So if it is rose at the end, then your polymeric material is agarose. So G50, now this 50 is determining the pore size and what size of protein or what size of biomolecule you want to separate will be the size of the analyte that you are going to separate will decide what type of gel you are going to use.
G50, the number here gives you an approximation of the size exclusion. So this is, will exclude proteins above 50 kilodaltons, 50,000 molecular weight. Inside is a white powder. In this beaker, I put 9 grams of the G50 powder, and I swelled the...
This process of swelling your powder in the buffer for several hours is equilibration. So you're equilibrating the conditions. Now the protein or your biomolecule will be, I said, is sensitive to pH. So your mobile phase, which is going to be your buffer, is going to be of that pH. Now, when you add it to the beads, it shouldn't be that it's a shock for the biomolecule, because they were actually in pH 7. And if you do not equilibrate the beads at pH 7, then for them, the environment is going to change drastically, and that might affect their activity. So equilibration is very important. And this is external as well as internal, because now the powder is going to swell. When you soak it, the buffer is going to enter inside the bead also. So the pH on the surface of the bead and inside the bead is also going to be the same. So for your analyte, which you're going to separate, these conditions are very, very important.
Powder overnight using this tris buffer, 30 millimolar tris buffer, pH 8.0. You can see that the 9 grams has swollen up to a volume of about 90 milliliters, almost 10 milliliters per gram of solid. Now I'm going to gently stir the gel. It's important not to stir this too vigorously. Don't mechanically stir this. That can break your gel particles up into very fine dust, which will impede your flow rate in the column. This is making a slurry. I'm using a sawed-off pipette to transfer my slurry to the column.
So the column already has a glass wool or a cotton plug at the bottom. So that's why he's able to add it. If there was no blockage below, whatever material you add from above will just trickle down the column.
For gel filtration, I want a fairly tall gel bed. So I'm trying to mostly fill this column. And excess buffer will drip out the bottom. So here you can see the drips coming out the bottom. Gel bed is starting to settle a little bit. Gel bed is right here. I'll add a little more buffer so that it doesn't run dry at the top. So I'm gently adding a little buffer to the top. This looks great. You can see the gel bed is fully settled here. There's a little bit of buffer on the top. I've capped the bottom right now to keep it from going dry. I'm going to put a mixture of 2 molecules onto the column. Blue dextran is a very large molecule. It's a polysaccharide. Molecular weight about 1 million. Fluorescein, on the other hand, is a small molecule. Molecular weight about 350 grams per mole. I chose these 2 molecules because they're nicely colored, so I'll be easily able to see the separation visually as they go through the gel filtration. I've drained the buffer, so now there's no residual buffer on top of the gel, and I've made a mixture of a total of 0.8 milliliters, 400 microliters of the fluorescein, 400 microliters of the blue dextran. Nice green color. I'll separate these.
So he has mixed those 2 components together. He has chosen those 2 components based on their size. Okay, you saw that there's a huge difference between the molecular masses. And before he is loading the column, he has removed the buffer, because you do not want to really dilute it too much. So just before you load your sample, there shouldn't be excess buffer on the gel bed. And this should be a quick process, not that you remove the buffer and start loading your sample after 2 hours of removing the buffer, because that might dry your column. So he has removed it just before he's loading the sample.
These on my gel. For this size column, this is getting near the maximum I would put on the column. I'm using a Pasteur pipette to gently load my material onto the column without disturbing the gel bed. So here you can see the blue molecules, the large molecules, are moving faster through the gel. So I'll hope that I can get it.
Yeah, so the larger molecules are of blue dextran. Now, because these are the beads now, the larger molecules could not enter inside the beads. So now they are making their way through the void volume, okay, through the voids, not volume, sorry, the voids between the two beads. So the interspaces.
A complete separation between the blue and the yellow. Now the excess on the top of the gel is all soaked in. So I'm adding buffer very carefully to the top of my gel filtration column. I'll just add a fraction of a milliliter first. Help get everything into the gel before I add a large volume of buffer. So now the separation is proceeded.
So first process was equilibration. Second was he poured it into the column. He allowed the beads to settle down, and then he loaded his sample. Now this is the time where he's allowing the binding or the absorption of the analyte into the beads. After that is done, then you start with the process of elution, that is removing the protein from the column. Okay, so he is now allowing it to bind.
Somewhat, I'm going to try to have a decently large volume this time of buffer on the top. About a milliliter would be great. If I do this well, then the buffer that I put on the top remains colorless because all the colored molecules have already gone into the gel. All right, now you can start to see a little colorless layer on the top. That's perfect. All the colored molecules are in the G50 and they're starting to separate quite nicely. The yellow molecules are up here, the blue are down here. Still got a little overlap. So I may have overloaded this column, but we'll see. I'm hoping that before.
Yeah. So yes, in the last class, I told you that the distinct separation must be achieved. Now, this is not distinct separation because they are still sharing the boundary. So the conclusion is that probably the concentration of the sample, the amount of the sample that was loaded on this column was very much higher as compared to the capacity of the column. So there is a ratio also. If the column is smaller, then you cannot load too much of volume of your sample. If the column is small, then the volume also has to be small. So what is he concluding? Because he's not seeing a distinct separation. He will achieve distinct separation only if the length of the column is higher, longer. Okay, now here the length is limited. Now that's what he concluded, that maybe the sample loaded was higher.
For the blue molecules elute, that they'll actually be separated from the yellow, but it's going to be close. So out of the bottom now, blue liquid is dripping. You can see I do have a colorless layer starting to develop here.
Yeah.
The fluorescein has been slowed down by the gel filtration. The blue dextran is coming through. So this technique is often used to separate a protein, which is large, from the small molecules that could be salts or could be a fluorescent tag that is unwanted. I've topped up with buffer on the top so that it never runs dry. The fluorescein is now eluting from the column. Fluorescein is fluorescent. I'm shining a little blue light, UV light on it, and you can see it glows green. The last little bits of fluorescein are emerging from the column now. Here's the fractionation. This first tube has nothing in it. So this volume, which looks to me about 2.5 milliliters, is called a void volume, where nothing comes out. But then the blue molecules, the blue dextran.
So the first tube that he has shown is containing your, basically your mobile phase, which is actually colorless. So that is the void volume. Okay.
Came through the column swiftly. So this is about a milliliter. Some of the blue dextran tailed into the next fraction. This is low concentration. Then I have a nearly colorless fraction here, and then the fluorescein starts coming out here. Fluorescein stopped coming out right about here. So the total volume will be 2.5, 3.5, 4.5, 5, 6, 7, 8, 9, about 10 milliliters is the total volume, which is what I would expect for a column of this size. Often what you want is just this first fraction with the large molecules. If you're trying to desalt a protein or remove the unbound label from a protein, then this is the fraction that has value. These fractions would just be junk. The original mixture, you can see, glows nicely. And what I believe is isolated blue dextran from the column has no glow in the UV. That's a sign that I have successfully separated out all the fluorescein.
In case of molecules which do not have color, because here there are two different compounds which are used, they have color, and one of which fluoresces in the presence of UV light. So when you pass the UV light, and if they fluoresce, then you know that it is a pure compound. So here he's checking whether the purity has been attained. Yes, he has been able to do that because there is color. Now, proteins or any other biomolecules without color, how are you going to analyze them? So you're going to collect the fractions as he did, and then you're going to probably take it for UV spectrophotometry. Okay, if it is a protein, if it's a nucleic acid, you know that if the UV light passes through it, you'll get the absorption readings, and then based on that, you will be able to decide. So for colorless, for the colorless solute or the analyte, UV is the best way to analyze whether you have achieved, whether you have separated your analyte or not.
From the blue dextran. So the column, if I've done it well, comes out completely colorless. It's reusable. Sometimes microorganisms like to grow in the cephadex. So if you want to preserve your column for a long period, keep it in the fridge, certainly. And
yeah, so the matrix is actually dextran, which is a polymer, and microorganisms, they can grow on that polymer. And that's why, again, never keep the column dry. You can reuse it after you have given thorough washes. So after you elute, and if you, when you are sure that now there is no more biomolecule or any other analyte left on it, then you keep some buffer over the gel bed so that it doesn't dry, and you can store this column in refrigerator, okay, or you can store it in a cold room. Usually the laboratories have a cold room where the temperature is very low, so you can store that column there in the cold conditions and never let it dry, so you can reuse it later.
sometimes azide is added to the buffer to prevent growth of microorganisms. Here's tris buffer with 0.01% sodium
So
azide.
sodium azide is actually antimicrobial. So you can add azide to the buffer, and you can then add that buffer into the column. So then there will make sure that there is no microbial growth or contamination in your column, because these are very expensive beads. So you do not want to really throw them. So take care of them.
And this will prevent microorganisms from chewing on the dextran that's in the column if you're storing it over a long period of time.
Okay, so any doubts here in gel exclusion chromatography? Have you all understood everything? So what is the basis on which gel filtration works? Can you please answer on the chat box before we start ion exchange chromatography? Is it on the size? Is it on the charge? Is it on the type? What is the separation based on? Size, Anushka. Yeah, correct. So who comes out first? The larger molecules or the smaller molecules? Who comes out first? Smaller molecules come out first. Prarthana. Smaller molecules stay inside the beads. The larger comes out first. Yeah, the larger ones come out first. Okay. So now we move on to ion exchange chromatography. Size exclusion and ion exchange chromatography also are popularly used to separate biomolecules, proteins also, because we know that they are made up of amino acids. Proteins are made up of amino acids. Amino acids also have charge. We can also separate them on the basis of charge. So we are now going to talk about ion exchange chromatography. Yeah. So if you have a mixture of molecules, now again, it could be a mixture of macro, micro ions. There could be these ions there in your sample, okay? Or it could be macromolecules such as proteins or nucleic acids. Now, the separation achieved in ion exchange chromatography is based on the charge that the particular, so basically separation is based on charge. Now, again, like any other column, ion exchange chromatography also has a stationary phase and a mobile phase. Okay. And this stationary phase is solid support and this mobile phase is liquid. All types of these chromatography that we are discussing are based on the interaction between the stationary phase and the mobile phase. So basically your stationary phase, like what we saw in the last gel permeation, we saw that the stationary phase has to be inert. Okay. So because this separation at the best can be achieved if there is a optimum, there is a desired interaction between the stationary and the mobile phase. So here the stationary phase is always fixed like all other chromatography. Even in the gel permeation chromatography, you saw that the beads that were the stationary phase, they are fixed. You do not change the volume of the beads. Similarly, you do not change the volume of your stationary phase also in ion exchange chromatography. You do not add extra later on, or you do not remove. You don't do all that. It's fixed. Okay. Now, the interaction between the stationary phase and the mobile phase may vary because who influences this change? This is the molecule that you are going to separate. So the analyte that you are going to separate on this stationary phase may actually affect the interaction between the stationary phase and the mobile phase. So here also you will see, just like size exclusion, some molecules will come out fast, some molecules will come out slow, and that is what you mean by separation. You're separating the molecules from each other. Now, when I say charge, it means that you are separating on the basis of, you can charge, polarity. Only polar substances or polar molecules that bear charge can be separated. Ions can be separated because you know ions are carrying charge. Especially like hard water sample. The hard water sample contains calcium, magnesium in a larger proportion. So you can actually remove these ions from the hard water and reduce the uh, water's hardness. So you can convert it into soft water or potable water. So now the stationary phase here is made up of polymers. Again, everywhere. Now these polymers, synthetic also and natural polymers also. So if you talk about natural polymers, we have starch, cellulose. These are the natural polymers. Okay. Agarose is there. Even in the gel permeation chromatography, we saw that agarose is used. Dextran is used. Dextran is also natural. Now, in iron, okay, we know one thing, that charge. We're talking about on the basis of charge. But the next word here is exchange. So charges are exchanged. In this kind of separation, we are working on the exchange of charges. So exchange of ionic charges between whom? Who is interacting? It is the stationary phase and the mobile phase that are interacting. So charges are exchanged among or between stationary phase and mobile phase. Okay. So here we know that when we talk about charges, there is plus charge and there is minus charge. So based on that, ion exchange chromatography can be of two types. So when we talk about ion exchange chromatography, there are two types based on the charges, because there is plus charge and then there's minus charge. So one of them is cation exchange and then the anion exchange. So cation exchange chromatography, anion exchange chromatography. So here it is the cation. What is the charge on the cation? Can you give me the answer in the chat box? So here the cation will retain on the stationary phase, and here the anion is retained. Okay, so let us take an example of cellulose as a polymer, as a stationary phase. Somebody has answered here. Yeah, correct, Anushka. So if you have, now what is going to happen here is, suppose I'm going to draw this. This is your matrix, or this is the support, the stationary phase. This is cellulose. Okay. Now this cellulose is attached to a positive, sorry, to a negative. So this actually is one unit. This is your stationary phase. Okay. So now if you have a column, again, it's a column chromatography. So obviously we are not going to achieve this without a column. The same things are followed. There will be a cotton plug. Okay, now you fill in your matrix. Now your matrix is cellulose. I'm drawing big beads so that it's very clear. And this is one unit. Okay. This contains negative charge. This is a negatively charged ion. Now what is going to happen is that there is another charge that is attached to it. So that can be some this. Now to a negative charge, who can attach? A positive charge. So this another moiety that is attached to your stationary phase is a positively charged ion. Now this positively charged ion is going to mask the negative charge. Okay, it is going to mask the negative charge. Now let me just increase the border of the column. So what is happening is, you have this is like a, I'm going to draw it like this. Okay, this is your column. So this now, so this is going to be your one unit. This is your stationary phase, the circle and the big plus sign. This is your one unit. This is going to be your stationary phase, and the attached star shape is an ion which is positively charged. Now, when you're going to add your sample and when you're going to run your mobile phase, because when you know now, you have seen the column, first you equilibrate it, which is in the mobile phase itself. Now you load your sample. So basically your sample that you have added on the column is going to mix with the mobile phase. So let us now consider that all the analyte that you want to separate has come into the mobile phase. So the mobile phase containing the protein is now mixed. Okay, now it will, whatever you have added, it's a mixture. So not necessarily that everything that you're adding into the sample is negatively charged, or everything is only positively charged. So it's going to a mix, it's going to be a mix of positive and negative ions. So now the positive and the negative ions are in the mobile phase. So what will happen? Let us say now you have added the mobile phase and this is a mix in the mobile phase. Okay, and there are some other ions also along with the green triangles. There are other molecules, other ions, and let us say that the charge on them is negative. So it's going to be a mixture. I've given you a mixture of proteins, and these they do not only contain a specific protein, they contain a lot of different things which carry charge. So suppose now what is going to happen, this mobile phase that you're running through, this mobile phase is now containing your analytes also. So mobile phase is going to interact with the stationary phase. After it interacts with the stationary phase, it will, there can be a possibility that now this is your, I'm now only drawing an individual reaction. So this was how it was before. Plus, after you added the mobile phase, now your mobile phase contained triangle of plus, rectangles of minus. So this might replace this. Okay, so now as a result, you will get a new combination plus and minus. So initially here, if you see, it had a star initially as a plus charge, but after you pass the mobile phase that contains your analyte, this exchange happened. So this is how fundamentally the ion exchange chromatography works. So now this will be binding to the matrix, or this will be binding to the stationary phase, and this star can be eluted, and even this can pass out in the elute. Okay, so there is an exchange in the ions. So after the molecule of your interest, which is say the triangle, which was here in green color in the column. So this, let us paint this as green. So now you got this. After the rest of the things that you didn't want have eluted, and the thing that you want, the analyte that you want, is now there attached, bound to the stationary phase, then what do? You have to now elute the bound molecule also. So the elution again is using a proper buffer, because if it is a biomolecule, it will be specific to pH. So you need to now keep adding your buffer to the column and elute the bound protein to it. Okay, so the same thing now you can apply for the anion exchange also. So here you might use, so this is going to be plus and this is going to be minus in the anion exchange, and this is going to be replaced. So for cation and for anion, vice versa, it happens. Now the applications are, they are used in separation of proteins, hemoglobins, biological molecules. They also are used in treating the hard water, because it is ion exchange. So I told you that there are calcium, magnesium ions in the hard water, so that can also be cleared off. So treating of hard water can be done using this technique. Now if you look again in this column, positively charged protein binds to the negatively charged bead. So this bead, this is going to be your stationary phase. and there is going to be a binding based on the charge. So then this one, these are the two different colors are showing the two different charges. So if it is a negatively charged stationary phase, the positively charged analytes are going to bind to it, and the rest of them which cannot bind, which repel each other, so the other will flow down. Okay, here I had another picture here. So if you look at this picture here again, the same thing is explained. So this is your anion exchanger. Okay, and then there is the binding between these opposite charges. Here also, it's a cation exchanger. So it will be attracted towards the positive, and then this bonding will remain. The rest of them which could not attach, the rest of them which could not cling to the exchanger will come out of the column. So we'll just see this video. I think you still have 4, 6, 7 minutes.
Hey everyone, quick biochemistry basics here. Let's talk about ion exchange chromatography. Ion exchange chromatography is based on the phenomenon of attraction between opposite charges. The stationary phase is selected such that it has a particular charge and attracts the sample molecules with the opposite charge. The stationary phase is also known as the ion exchanger. The ion exchange chromatography is widely used for the separation and purification of proteins, peptides, nucleic acids, polynucleotides, etc. The ion exchanger can be of two types, cation exchanger and the anion exchanger. Cation exchanger has a negative charge and attracts positively charged cation, while anion exchanger is positively charged and attracts negatively charged anion. Different functional groups such as carboxyl, carboxymethyl, sulfo, sulfomethyl, etc. can be used as a cation exchanger. Buffers having negatively charged ions like acetate, phosphate, etc. can be used with cation exchanger. On the other hand, functional groups like aminoethyl, trimethyl aminoethyl, etc. can be used as anion exchanger. The buffers used with anion exchange.
So these can be your stationary phase because you need a positive stationary phase. So these are having this positive charge, so they can be this can be the exchanges, and if they are positive, then the buffers also have to have a positive charge.
Exchanger has a positive charge, for example, tris buffer. Let's try to understand the separation of proteins with ion exchange chromatography. At isoelectric pH, the net charge on the protein is 0. That is, proteins have equal number of positive and negative charge. If the pH is shifted 1 unit above the isoelectric pH, then the protein will have net negative charge. And if the pH is shifted 1 unit below the isoelectric pH, then the protein will have net positive charge. Before proceeding further, it must be checked at which pH the protein is stable. If the protein is stable at pH 1 unit above isoelectric pH, then anion exchange chromatography is preferred as the protein will have a negative charge. And if the protein is stable 1 unit below the isoelectric pH, then cation exchange chromatography is preferred as the protein will have a positive charge. Once the protein binds the stationary phase in the column, elution of protein can be done by changing the pH or by changing the ionic strength.
Yeah, so when we have seen, I've been telling you about elution, that you use a buffer for elution, but those buffers can have different, you can use different conditions for elution, because the binding of the protein molecule to the stationary phase, the strength of the bond can vary, and to remove the protein To break that bond and to elute that protein, you might have to alter some conditions. So here you can use a buffer. So while binding the protein to your support, to the stationary phase, you were using pH 7 buffer because that was the process of binding. That was a step of binding. But for elution now, you can change the pH, say from 7 to, you can either go to the alkaline side, make it 9, or you can go to the acidic side, make it 5. Okay. But all of this depends upon what is the stability of your protein in those pHs. Suppose if my protein is very much stable, if the protein that I'm working on is very much stable at pH 7, and if I elute that protein at pH 5, it will lose the activity. If I also elute the protein at, say, at an alkaline pH, it might reduce the activity of the protein. So I may attain purity, but I may not get the active protein. Okay, so I will have to do several experiments. I have to do several trial and errors. So say from 7 to 9, if I decide to bind the protein at pH 7 and I want to elute the protein at pH 9, then I have to take intermediates. I have to do elutions at different pH, 7.2, 7.4, 7.6, so on till 9, and see that which is the pH, elution pH, which is not affecting the activity of the protein, and then choose that. So all these experiments initially are done on a very small scale in the laboratory, on a very small scale, so that you do not waste too much of matrix, you do not waste too much of protein also. You can also change the ionic strength. So sometimes binding is done at 10 millimolar. The buffer strength is 10 millimolar. But when you elute, you can increase it to say 50 millimolar or 100 millimolar. You can increase the strength of your buffer also. So that might also help in elution. Because when you increase the strength, you are going to increase the certain number of charges. Okay. And then when you're doing ion exchange chromatography, it is all about exchange of charge. So then that can work here. We will also see this in detail in the next class. What do you mean by salting in, salting out? What do you mean by changing the pH of the elution buffer, changing the ionic strength of the elution buffer? We are going to see that in the next class. Okay, that was the end of it. Oh, this is not working. Okay, are there any difficulties so far? Have you understood everything that we discussed today? I will share the link to this recording. But is there any doubt, any questions? Hello.